Okay, everyone. So as far as the second midterm, I said the midterm is 21st, November 21st, the Monday. Okay, so mark the calendar. Yeah. It's gonna be chapter 3. And I guess still you can bring one sheet of paper. So like before, so one page you can bring. Second.
Calculator, no calculator, please.
Okay, very good. So let me, without further delay, start. The last thing that I did the other time was Parseval's theorem. Then basically, if you look at the energy in the time, which is the integral of the gt squared, this is the energy in the time, is equal to the energy in the frequency. So in the frequency you have gf, so take the magnitude of gf squared, take the integral, and these two are equal. Let me solve an example for that. And today we are going to actually talk about also, again, the energy, but something related to energy, which is called the energy spectral density. Okay. So what's an energy spectral density? By the definition, it's nothing but just for a signal that you have gt, then you have gf. So you have gt, the time, take the Fourier transform, you get gf. It says, okay, just look at the magnitude of gf squared. I mean, nothing very complicated. Magnitude squared, just call this psi g, and it's a function of frequency, right? So call this energy spectral density. Energy spectral density. ES. Okay, so just the squared of the magnitude of g. Now, by the definition of EG, we saw that in the Parseval theorem, we can say it's the magnitude of GF squared df. And this part is actually that side, the density. Okay. So basically, the energy, this is the whole energy, and this is the density of the energy. So therefore, so for example, if I plot psi gf as a function of f, let's say this is a function of f.
Thanks.
So the integral, the whole integral gives you the energy. If you take the integral from minus infinity to infinity, that's going to give you the energy. But also, you can look at like maybe different frequency or a range of frequency and say, what is the energy from f1 to f2? For that, you can also take the integral. So again, like this is like a density function. So if you take the integral from f1 to f2 of this side G gives you the energy in frequencies from F1. Okay, and if you take the whole range, then take the integral of the whole range, is the total energy. Okay, so that's the definition. So in the previous example that we saw, I guess this is related to, anybody remembers what is GT for this? If this is GF, what is GT? This is something,
E raised to the negative 8.
yeah, e to the power, this is the pair. If you take inverse of that, you get e to the power of minus 18. Okay, this is something that we are going to see a lot. Because it's a simple, like it's a symbol in the time, symbol in the frequency. So hopefully you can recognize this. 1 over a plus the number s in. Okay, good. So if this is GF, what is the now the ESD, the spectral energy, spectral density? Just take the magnitude of GF squared. What's the magnitude of GF? It's the magnitude of the numerator divided by the magnitude of the denominator. The magnitude of the numerator is 1 divided by the magnitude of the denominator. What's the magnitude of this?
Square root of a squared plus 2 pi f squared.
2 pi. Okay. And then because the whole thing is a square, so that takes care of that. So this is the energy spectral density. Just take the magnitude of the Fourier transform, a square. Very simple. So anybody remembers what's the definition of a bandwidth? Let's forget about this slide. What's the definition of a bandwidth? For a signal g of t, correspondingly, if I take the Fourier transform g of f, what is bandwidth? Anybody remembers?
It's a point where the cutoff frequency is.
The point there,
Where the cutoff frequency is.
cutoff frequency. What do you mean by cutoff frequency?
1 over square root of 2.
No, that was called something else.
No, that's just.
That was just the cutoff frequency.
Is it just the range of frequencies?
The range of frequency, the maximum frequency that they have. So let's say if I have a spectrum like that, it is a g of f. Okay, and let's say my f max is 10 kilohertz. We will say this signal has a bandwidth of 10 kilohertz. Okay, so pay attention to this. The maximum frequency that you have is called the band. And you look at it as a frequency, not in the time. In the time is duration, so you have similar thing in the time. So you say the duration of a signal, let's say if you have something starting from 0 to 10 seconds, you see this is the time duration. In the frequency, we call it bandwidth. Okay. However, most of the time, what happens is that the bandwidth is actually infinity, meaning that I don't have this exactly after some frequency, everything is 0. What's the case is that I have something like this. So it goes to infinity. Like, sorry, not goes to infinity. Like, f goes to infinity, I mean, it still has some values. So what's the bandwidth here by that definition? Infinity. Because that definition says the bandwidth is there. After that, GF is 0. But here we have a signal, right? So the bandwidth is infinity, BW. However, it's not practical to say this signal has an infinite bandwidth because after some frequency, it's going to 0. So one definition is to look at the energy of the signal. Okay, basically look at this energy spectrum and say, I consider my bandwidth where I have maybe 95% of the energy. If my energy is 95%, I consider this as an approximation for my bandwidth and use that. So that's called the essential bandwidth. Okay, so essentially this is my bandwidth. And this depends on application. One application might be 95%, one application might be 9%. Really depends on your application. And see, so the essential bandwidth B can contain 90%, 95%, or even 99% of total energy. Okay. So let's go on next section. And this case that this going to infinity happens a lot, especially when you have something which is finite duration in time. Finite duration in time. Anything which is finite in one domain, it's infinite duration in other domain. Infinite duration. For example, remember the pulse signal, right? So for the pulse in the time, we had a finite duration. 2 seconds, 3 seconds, whatever. What was the Fourier transform? Sinc. Sinc goes to infinity. Okay? And vice versa. Here, if you have something going to infinity, if you have a sinc in the time, you are going to get a finite thing in that frequency. So always remember this. If you have something finite in one of the domains, okay, for the other domain it's gonna be okay. So now in the lab, when you make a signal, definitely it's gonna be finite duration. Okay, so you have a pulse for 10 seconds or something. So therefore, the Fourier transform gonna be from minus infinity to infinity. But then the essential bandwidth can define essential bandwidth. So I make a point here. The bandwidth is infinity. Because going to infinity. However, the essential bandwidth you can have a different essential bandwidth. Make sense? Okay, so the two things you to remember here. Always if you have a limited signal in one domain, limited time or limited frequency, in the other domain you are gonna have expanded to infinity. This is one thing to remember. The other thing, the definition of the essential bandwidth, that you take the integral of the power spectral, energy spectral density, and if the energy is 90%, we're going to say, okay, this is my essential. So we're going to see one example of this. But let me just see here. So most practical signals are time limited, so their spectra spans to infinity. Yes.
Will they tell us what energy we need to make it like 90%, 95, or 99?
It depends on the application.
Right, but like in the question, if they tell
Yes,
us like find
yes,
the bandwidth,
definitely,
they'll
yes.
tell us what that is.
Yes, I'll tell you, for example, I want to find the essential bandwidth for 90 containing the 90% of the energy. Okay, so most practical signals are time limited, so the spectra extend to infinity like that. However, since the energy is finite, the energy is finite, so definitely the integral should be finite, so it means that the tail of this approaches to 0. As f goes to infinity, so definitely this is going down. So at some point I can neglect it. So above some frequency bhertz called essential bandwidth, the frequency command can be neglected, and that's how we can find the essential bandwidth for 90%, 95, or 99% of the total energy. So now let's look at this example. So read the question. It says estimate the essential bandwidth of the signal e to the power of minus AT with t, again the famous signal, if the essential bandwidth is required to contain 95% of the signal energy. So I have GT, I have GF, and I know the total energy is like this. We calculated this the other time. The total energy is like that. Now I'm gonna find the essential bandwidth for having 95% of this total energy. For that, calculate the energy spectral density or magnitude of GF squared. Okay, very simple. We know the magnitude of GF squared. Just calculated that. If you plot it, it's gonna look like this. Now what should I do? So again, if you look at the bandwidth is infinity because this is going to look. Either you want to cut it such that this is 95% of the total energy each. So basically what we have to do, we have to take the integral, this is the area, right? The area behind this. So take the integral of this thing, or we can just alternate it to squared, magnitude squared. Take the integral from some minus b to b that I'm gonna find out, and this should be equal to what? 0.951 the whole easy, and we know it's 1 over.
Easier to do.
So we have to just take an integral. We have that. Any question here? So again, remember the energy in, like, for finding an energy in some frequency, you have to take the integral of f squared, like the square of the yes, the energy squared side. That integral gives you the energy in that part. Energy in F1 left. And now the energy from minus P to D is just the integral from minus P to D of the side. Okay. So now I have to take the integral of this. Anybody remembers what kind of signal it would be the integral of this? That's not very tangent, yeah. Tangent inverse. So just replace here that signal. So I have it in my slide. Okay, so the energy should be 95% of the total energy. And the integral of this happens to be tangent inverse. Okay, so tangent inverse, and then put the limit from minus b to b. Just replace it. We're gonna get this one. And from this equation, you can just find it. So if you happen to be 2.028 hertz. Okay. So it goes to 8 hertz. Okay, this is where from this frequency minus 2 hertz to 2 hertz, I have 95% of the energy. Okay, so this is what the energy is. How to find the energy from minus 2 to 2. This is the energy, and then 95% of the total energy. Any question here? Question here?
I was wondering how the math worked out on that one.
The time the integral? Yeah, that's so we are dealing basically with the integral of 1 over 2 times f squared.
What about the 0.95 over 2? That's
What's that?
0.95 over 2.
Yeah, this is 1 over 2a. Yeah.
Okay, and then 1 over
1 over 2 is the total energy.
We're trying to find out how you got the 2.02.
Yes. You have to take the implicit integral. See, minus b to b of this integral, which is at this integral, is equal to 0.95 over 2a. Okay. Now, this integral you have to go to the table and have apparently the tangent inverse. Guys, you're asking, right? Okay, yeah, so if you go to the tables of the integral form, you will find something like that. 1 over x squared a squared dx is kind of tangent inverse of maybe some x over a or something. I haven't memorized that. But please do that at home. It's a good exercise. So here's just the final answer. Tangent inverse of 2 pi f over a. And then divide it like that. Yeah, please figure it out how the integral of this is. That shouldn't be very hard. So the integral of x squared plus a squared dx. Look it up. Probably at the end of your book you have. So other than the integral part, everything else is clear. Guys, you're fine? So 95% of the total energy. This is coming from that. And this is the energy of the now you have to do the rest. Okay, now what should I do after this one? Anyone can tell me? It's like, okay, let's say I know this and this is what to do that. So what's next? How can I solve this one finally?
Multiply by pi.
So first of all, a and x cancel. Multiply by 5. Okay. So now so far I have tangent inverse 2 pi over a is 1 and remember, we want to solve it for what should I do?
Take the tangent of both sides.
Take a tangent. Take a tangent of both sides. And when you take a tangent of both sides, tangent and tangent inverse cancel each other out. So you get 2 pi over a equal to tangent of t. And then that after that, we just want to find is a over pi. So that's how they get that number. So after the integral, we are not done because we have to find b. This is how to find b. Just take tangent and get rid of the tangent inverse of this side. Everybody got the last thing? It's just a simple, one. Okay. take the transform,
Yeah, taking the transform of the E, negative AUT.
okay, Fourier transform, yeah, we have it here, right.
Once we have that transform, we just multiply by 0.95%.
No. So what do you mean by transform? So you have GT, which is B minus AT, and take a Fourier transform, okay, you get GF. GF some complex. Okay, so GF itself is like that. And then multiply this by 0.95? No, you have to, first of all, you have to know what's the whole energy. How can we calculate the whole energy? Using the integral from minus infinity to infinity of magnitude GF squared here. From the parcel of the side, right?
Right. Can we find it in terms of T as well?
Yeah, we can do that,
And
but
then-
anyway, we are gonna get the same thing. Yeah, if you put here GT, you can do that. GT squared GT, you are gonna get the same 1 over 4. That's fine. But that will just give you the whole energy, not the band, not the 95% value. For that, you need to take the integral of that. Okay, so now please check this example in your book, 3.21. Please take time, I don't know if you're in class. Please check it out.
Thank you for
Yes.
confirming that. Thank you.
Oh, sure. That was your question?
Yeah.
Okay. So now, let's look at the AM modulation that we had and see what happens to the energy of the signal after modulation. So as I recall, what was AM modulation or amplitude modulation? I had my signal and I just multiplied by cosine. So to show you what we had, we had the signal g of t, and we would multiply by just the cosine some carrier frequency, if not. So that's the GT, the cosine, and when I multiply it, I get this. Remember the envelope T and all those things. And anybody remembers what is the spectrum of these? If the spectrum of GT, capital GF, the spectrum of this modulated version is shifted to the right and to the left, right? And divided by 2. So basically, this is the spectrum of GF for the original signal. After the modulation or multiplication by cosine, you're going to have 2 replication of that on the depending on the carrier frequency. If the frequency is F naught, so one goes to F naught, one goes to negative F naught, and then divided by 2. So this is what we call it amplitude modulation. So now let's see after doing amplitude modulation, how does the energy of the signal changes. Okay, so let's call this P of G times cosine. Take a Fourier transform, as again you know, the Fourier transform of the P is G of F plus F naught, F minus F naught divided by 2. This is the Fourier transform of the modulator. Now I want to look at the energy. For that, let's look at first of all the energy spectral density. So as I recall, the energy spectral density psi GF was nothing but just the magnitude of GF. So I have to find the magnitude of this signal squared. transform of that. You have to find the magnitude of that. And then it's square. Okay, good. So I have g of f plus f naught and f minus f naught. So basically what I have g of f minus f naught and then have g of f plus f naught. So now take the magnitude and let's square. What do you think would be the case? If I take the magnitude of that, let's square. Any idea? So I take that one, let's square.
Is the magnitude the 1/2
No, the magnitude is the magnitude of the whole
of the
thing.
entire thing?
Yes. So in general, if I have magnitude of x plus y, can I write the magnitude of x plus magnitude of y? Yes? No. Right? Or you can write it like this. Can I do this? No, because you know when you square things, there should be another term like 2xy and z. Okay, so in general, I cannot. It's not simple to just say this plus this is squared plus that is squared. However, in this case, because they don't have an overlap, squaring the whole thing is as if I square this and square that. I hope everybody like this because there is no overlap. If they were like overlapping like these, I could have said, okay, I squared this and I squared it, I had it. But now they don't have any. Okay, so please make a note here. I guess I also have it here. Since these two do not overlap, this squaring that means I can square each element. I square this plus square that. And 1/2 also is squared, so I get that. Okay, good. So therefore I get 1/4 of magnitude of g of x plus f naught squared. So this is nothing but just the side shifted by f naught, and then this one again another side. Because remember this is the definition of stuff. Magnitude g of x squared. Now instead of f I have f minus f naught or f plus f naught. So just after we just change this to f plus f naught. So this is the one result that we got therefore. The energy spectral density of the modulated signal is 1/4 of the energy spectral density of the shifted version of energy spectral density of G and another quarter of that. So in the figure, this is the case. This is side G, the signal, original signal. This is side phi, or side, which is quarter of this, quarter of that. If that's K, this is K over 4, so quarter, and then just shift it to X, quarter, this side. So by modulating the ESP, this is the ESP of original of GT, this is the energy spectral density of the modulator. So this is what happens. Scaled by quarter is shifted here. Now how about the energy? This is ESE. How about the energy? For energy, you have to take the integral. Okay. The energy, so let's look at, this is EG, and the total of this is EF, so E. What do you think would be the relation to the energy?
They're equal.
How about if you compare just these two? This is K, this is K over 4. So if you take the integral, if this area is A, let's say, or G, what do you think this area would be?
Quarter A.
Quarter of F, right?
So that's two of those.
Yeah, so this is A over F. Because I just scaled it by 4, and so when I take the integral, let's say I take the integral of x of t. Now if I multiply it by quarter, then it's gonna be 1 quarter of the original t, right? Okay, so I scale this by 4, so I get A over 4. The same here. So what's the total energy? A over 4 plus A over 4, which is A over 2. And that one has like 8. So basically, the energy after modulation is divided by.
Where does it go?
So you have g of t multiply by cosine to get the t.
Dissipated as heat.
Yeah, you have to let it know, you have to think more. Where does it go? But that's not very simple because the cosine has also some energy. Okay. This also has some energy. So it's not that this is only energy of this. So it's the question is more maybe complex than that. I'll think about it. I don't know. Where does the energy go? So you have a signal, low frequency, like that, and then you multiply it by cosine. So you get this kind of.
The bandwidth of the increases.
I mean, look at this. Like, if I multiply, I have a signal. If I multiply by 0, let's answer this. I had a signal. It has a lot of energy. I multiply it by 0. What do you get?
0.
Where does the energy go? It's the same thing. It's like when you multiply 2 by 0, you get 0. You cannot say where did the 2 go? You multiply it.
Is it just the math, or is it?
Yeah, maybe there's some physical interpretation on that. I'll think about the physical interpretation. But math-wise, I mean, you have a lot of energy, you multiply it by 0, then you get 0 energy. You're basically
Destroying it.
yeah, destroying it, exactly. Maybe as a heat or somewhere, it disappears. Yeah. Good question, okay, fine. So now. Okay, this is the mathematical way of just what I did. The energy of the whole thing, which I mentioned at A, the area is EG. For the other one, is quarter of this integral plus quarter of the integral is little ones, quarter here, quarter there. So the total is half. The quarter and quarter is the half of the energy. So energy of the modulated signal is half the energy of the base structure. Okay, I look at here. So the integral, so here my function was shifted. How can I take the integral? If it was like only, I don't have f naught, I knew what's the integral. It's just the energy. But I have f plus f naught. Does it make a difference? so my question, I repeat my question. I know that the integral of this psi f df is the energy. So how about the integral of psi of f equals 2? Why not? I shift psi by amount of 2. And I take the integral. What would be the same? Good. The same, because again, like, instead of having these, I shift it. And then take the integral. I don't change the area. Mathematically, you can say, okay, I do a change of variable instead of f, I do f prime. Do the math, it's going to be the same thing. Okay, so that's why here, this is exactly equal to, if I say, any question here? So, let's just put 5 over here. This is 5 over here. Where is power?
That's strictly for AM modulation?
For the other one?
Is that AM modulation only, that it's half the power, or?
Yes, yeah. For FM, you're gonna study probably the next chapter. Yeah, if you multiply by cosine of sine, the same sign. The energy will be half. Okay, so anybody remembers the autocorrelation function from chapter 2? You know, when we wanted to see if two signals are, let's say you had two signals G and H, and if you wanted to see how similar they are, if you remember, you would say, okay, I correlate them, let's say G of T, and then maybe H of T plus tau, something like that. Remember, and then we start, and we call it psi T H. Anyone remember we call this cross correlation? Cross correlation. And then we had autocorrelation, which was when you consider your original signal and another shifted version of the signal, and you correlate them to see how similar they are. We call that psi of G. That was the autocorrelation. To remind you, there was an example that we send a signal in a radar, we send a signal, and then the signal comes back, and we wanted to see the delay. We would correlate these two signals together and see how they are different or how the delays, how much I have to shift this to become similar or something like that. So anyway, so this was the definition of the autocorrelation. You get the signal, and then you shift it, and then correlate them. And we had the example that the cross correlation or autocorrelation might look like this. First of all, it's symmetric, and usually, always it's maximum at the tau equal to 0. Can anybody tell me why this is maximum at tau equal to 0? Tau is the amount of the delay. So when tau equal to 0 means that I'm correlating the original signal with itself, not the shifted version. So that should have the maximum correlation. Okay. So as I shift more and more, again, this is my original signal, and then this is GT, this is G of T plus tau. So as I increase tau, probably the similarity decreases. So somehow this shows the measure of similarity of the signal by itself. over time, how to say it? Okay, so we had a lot of, I guess, study over that, chapter 2. But here, just look at here, the definition again. Again, the autocorrelation is nothing but just the integral of gt times dt plus tau. So again, I'm correlating g of t and its shifted version. And we call that psi. Which is a function of tau. So please correct your note. This is a function of tau here. It's not a function of t because the t is the variable here. I take the integral. But what is left is tau, the amount of the shift. Okay, now interestingly, we are going to prove that this autocorrelation and this energy spectral density, that is the same notation actually, capital psi, they are the Fourier transform pair of each other. Okay, so the autocorrelation before the function of time. Autocorrelation. If you take the Fourier transform, you get that energy spectral thing that we're talking about. GGFS squared. IGF squared. Yeah, the Fourier transform pair. And that's why Paul uses the same side to show the relationship. Okay, so let's prove this. Okay, so we're going to take the Fourier transform of t and prove that it's not that. Take a Fourier transform of this. The whole thing comes here, times the minus j 2 pi f tau. Everybody agree? So this is the whole signal that I want to take the Fourier transform. So it comes here. Okay, remember, for example, if this was g of t, then we'll take the integral of gt e minus j 2 pi f t dt. Okay, the same. Multiply by this, take the integral. Okay, now that we have two integrals, the usual trick that we have, and this is the third time that we actually are seeing this trick. What should I do? I have two integrals, and then you see e minus j 2 pi f tau is outside, and you have that. What should I do? Any suggestion?
Bring the exponent in.
Very good. Bring the exponential in. Why? Why can I do that?
Because of the linearity of the integration.
And it is not a function of t. It's a function of tau. Okay, for t, that's considered constant. So I take this in. Right. So let me write. So therefore, what I have now, I keep that exponential term inside, so I have now two integrals. E minus j 2 pi and tau, gt plus tau, et. Okay, so now anybody can tell me what's next? What's the second step of the trick?
And with respect to tau.
Yeah, you switch the interval.
Switch the
And
integral.
then
Right.
the tau.
So it's always three steps, like take like the one outside, inside the other integral. Take this inside, and then second step switch the integrals. So meaning that I switch these two. So if I switch these two, I have the tau here and then the t. Now I'm considering for the integral thing, I am in front of tau. So what else I can take out?
GT.
Now g of t is not a function of tau. It's a So that's very interesting. First, I took this inside, I switched it. Now this is not a function of tau, I can take it out. Okay. So again, this is very, very common. We're gonna see, at least you have seen it 3 times. So now I take it out, and let's see what happens after that. Okay, so here you see, please make a note here, I mean, in case that you're reading at home, and see what happens. I take that one inside, I switch these two, and then now I'm a function of tau, so dt can easily come out. Okay. So let me call this h of tau, function of tau. So integral of h of tau e minus j 2 pi f tau d tau. So that's the Fourier transform for. So that's the Fourier transform for what? Forget about this. Assume instead of this, I have some function h or g, whatever. Let's say g. I'm familiar with g. G of tau e minus j and tau d tau. What's that? Fourier transform. Remember, gt e minus j 2 pi ft. That's equal to Fourier transform. So therefore, the whole thing here is the Fourier transform for this h. So this is, as I said, Fourier transform of this h of tau, which is g of tau. Okay. So Fourier transform for g of tau. So now if the Fourier transform of dt is gf, then anybody tell me what the Fourier transform of g of, here the variable is tau, g tau is gf, what's the Fourier transform of g of shifted version? Which version?
F minus F naught or something.
No, when you shift in one domain, what's the corresponding to?
Exponential.
Multiplication by exponential. Very good. Shift in one domain, multiplication by exponential in the other domain. Shift in the time, multiplication by the amount of shift. Okay. So let's hear it. Okay, good. So this one is the Fourier transform of this, and then the Fourier transform of that because of this. I mean, shifted version you have this. And we can just see that. So you have gf exponential, and then you have integral of gt. Gf comes out, and then this is nothing but just minus. I will just talk about it the other next time. So I'm going to take a quiz and we won't have enough time. Anyway, so we almost there. So we prove that the Fourier transform of the autocorrelation function is the energy spectrum of this.
Alright, here you go.
So please take everything.
If it comes out clear without autofocus messing things up, I'll probably just use it here instead.
Wait, did you turn on autofocus?
No, you said it last time.
Oh, no, it's just that it's not autofocus, it's that that's within the focus range, but that's too far away.
Yeah.
You're saying just switch seats next time, that's fine.
It comes up clear, visible.
Alright. And you hit stop and it said saving and stuff?
That's why I still